Welcome back to AP Chemistry, everybody, and this is still Unit 5. We're taking a look at electrochemistry, and to this point we've always been taking a look at one part of electrochemical cells, and those are going to be your voltaic cells, otherwise known as galvanic cells. And those are going to be the spontaneous types of reactions. Now you'll notice that this particular experiment we have a power box because we're going to be looking at another type of electrochemistry which involves non-spontaneous reactions, and those are your electrolytic cells. Okay, so first of all, to make a parallel circuit here, notice that I do have a bridge between my black and my red in the middle in here, but then I end up with a black side and a red side over here, and I know this is a red cord, but envision this to be a black cord going there, and that's going to help with figuring out what's going on. My black cord is going to be going to a sheet of copper metal. Okay, so this copper metal is going to serve as one of my reagents here, and that metal sheet is going to be my anode. Okay, we're going to be taking a look at taking this copper metal, and I'm going to be stripping it away, adding electricity, so it strips away electrons and forming copper ions. So with that, I'm going to take my my alligator clip that's attached to my black cord, my black outlet here, and I'm going to be taking my copper after I've washed it off with my acid and base that was provided in lab. I'm going to put this into my solution. Now this actually plating solution does have extra copper ions in there just to kind of boost it a little bit, but essentially what we're going to be doing is calculating how much of this copper is going to be lost, and it's going to be deposited onto this key. Now this is a metal key, and I'm going to be forcing the copper ions through adding electricity. I'm going to be forcing the copper ions to actually plate on here, and we can actually figure out the mass of copper that's going onto here and apply Faraday's equation to calculate exactly how much has been there. Now I've also washed off this key with my base and my acid, and so we just have to have a method of taking the metal and dangling it down as well. So I have a copper wire in here. I made just a little hook so I can retrieve it a little bit easier, and to allow it to sit into the solution even better, I can, without putting the electrodes from my power source in there directly, I've dangled it with a glass stirring rod. Okay, the glass stirring rod does not conduct any electricity, and so I use glass for that, but then I can just take my positive, my red clip, and clip it to the wire itself. The wire will be conducting. I do not have my key or my my copper sheet touching one another within the solution. Okay, so this is all set up and ready to go. Now let's think about what's going on here. Okay, I have the copper itself, the copper sheet, is going to be oxidized at the anode. Okay, and what's going to happen is I'm going to force it to lose some electrons, and that will actually release the copper ions into solution, and we're going to be putting the red reduction at the cathode. So the copper ions are going to reduce right on this end, and that's going to actually plate the copper the copper ions. It's going to reduce that into copper metal, and that'll plate right onto the key itself. So remember, we have the metal key that's here sitting in solution, and basically I'm just waiting to turn on the power source to start to force those electrons to go. Now you'll notice that I've got it all set up and ready to go. I've got everything else clear. I simply turn the dial, and I'm going to turn this up to 20 on the gauge itself, and that way I can actually calculate the volts that's in there. And we will need to start a stopwatch with this because we're going to be with Faraday's equation. We take a look at the coulombs, we take a look at the time, and we'll be able to calculate then the mass of the copper that's going on there. So while that's running a little bit, notice that we have an initial mass of our copper. We have an initial mass of our key. We have a final mass of our key when we're done. We can see the change in there and the initial mass of the copper sheet itself, the electrode, and the final mass, and we can see there. Then we take a look at the current, which is amps or coulombs per second, the amount of time that we did in minutes and seconds, and then we can take a look at how many coulombs were transferred, Faradays were transferred, the moles of electrons were transferred, moles of copper that were deposited on the key, and the moles of copper that were lost by the strip. Law of conservation of mass says that these two should be equal to one another, and we can actually calculate the amount of deposition based off of the electrons being transferred. Okay, so it doesn't take that long to run with that. The longer you run it, obviously the more copper that's going to be on. The end product is pretty cool. We're going to end up with a copper key that looks like this. And the question is, how thick is this? Okay, how many centimeters thick? If we knew the size of the atom and all that, we could actually put how much is actually plated on top of there. So that's the lab setup as we go. You'll notice if I turn this off, even the short amount of time that I had with there, you see that, wow, there's a lot of copper that actually deposited on there. So it's a very quick procedure that we find with there, but obviously the longer we would have that running, the more copper would be deposited. Okay, so that's the lab setup that we've got going on here. Have fun with the electroplating with Copper Lab, but also remember, you got to collect some data as we go with it, because there is going to be some calculations using Faraday's law. All right, good luck, guys.